All right, welcome to the third presentation of the ATiA seminar, Applied Topology in Albany. We're delighted to have Elchesen, who is a graduate student working with Peter Bubenik, who should be on the job market next year. So please keep your eyes out for Alex. Really excited to hear about this work as it seems to relate to a growing theme across applied topology, which is how Möbius inversions show up in persistence diagrams. All right, take it away, Alex.
Yeah, thanks, Justin. Thanks for having me. So I'm going to talk about this idea of having persistence diagrams with negative points, and in particular, extending Wasserstein distance to such objects. And then at the end, I threw in universality, which is something that we were working on sort of concurrently with this project, and actually that grew out of this project. And they relate somewhat, so I'm going to talk about those two things. So the first part, we're going to talk about extending metrics to signed settings. So the original motivation for us was this idea from Leo Betthauser, Peter Bubenik, and Parker Edwards, who are all people in my group. So they considered the graded rank function. So if you have a persistence module, so we all know what the rank function is, you can consider the graded rank function. So for k bigger than 1, you assign the kth graded rank function to be 1 if the rank of the structure map from A to B is at least k and 0 otherwise. Okay, so here's a really illustrative picture. So on the top, we have the ordinary rank function for corresponding to a certain persistence module with this persistence diagram in blue. And then on the bottom, you have the 3 graded rank functions. You have graded rank 1, graded rank 2, and graded rank 3. And so really all you're doing is you're essentially just rewriting the rank function in unary decimal or notation, right? So you're saying, okay, like if the rank is at least 1, we put a 1 there. If it's 2, we put a 1 there. And then if it's a 3, we put a 1 there. And then if we add all these together, we just get the rank function back. So we're just decomposing it into its unary representation. The interesting thing, so we know that Möbius inversion of the rank function gives the persistence diagram. So kind of the interesting thing is that, what happens if you Möbius invert this graded rank function? And so what happens is you get, I guess, what we call virtual persistence diagrams. So you get what they called graded persistence diagrams, which are sort of like persistence diagrams, but you can have multiplicity +1 or -1. So in this picture, so again, on the top you have the rank function, and then if you Möbius invert that, you get the persistence diagram, which are the blue points. On the bottom row, you have the graded rank functions, and then the blue and green points correspond to the Möbius inversion. So you get these graded persistence diagrams. And so kind of the really interesting thing is that actually these graded persistence diagrams are completely equivalent to the persistence landscape. So the positive ones in the graded persistence diagram correspond to the local maximums of the landscape, and the negative one corresponds to the local minimum. So this is like just kind of another perspective on the persistence landscape, is that you can obtain it by Möbius inversion. So that's kind of cool. And so kind of like when I joined the group, the question was, okay, what kind of distances can we consider between these things? I mean, obviously we have like, the L2 distance between persistence landscapes, but if we want to think of these more as like persistence diagrams or signed persistence diagrams, what kind of distances can we consider between them?
Wait, Alex, could I ask what you mean by local maximums and minimums?
Oh, just for the persistence landscape. So the blue point correspond to the local maximums of the persistence landscape, and the green point corresponds to, I don't know if you can see my mouse, but the green point corresponds to the local minimum of the landscape.
Yeah, I think maybe it might help to just briefly recall how the persistence landscape works. just in case some people on here haven't seen that.
I wish I had a picture, but
and we do see your mouse, by the way.
Oh, okay, that's good. So maybe I could draw it here. I don't know if this is the best way to do it, but so basically the persistence landscape, you sort of take your persistence diagram and you look at sort of envelopes. So you're looking at sort of this outer envelope.
Mm-hmm.
Okay, except you turn this picture sideways. So you just rotate by 45 degrees. This outer envelope corresponds to the first persistence landscape. And then you throw that away. So you throw away all the ones, and now you look at sort of the next sort of inner envelope. You draw that. So that's the second persistence landscape. And then do the same thing here. So you get the third persistence landscape. So basically what you get is a sequence of functions. You get lambda 1 is the lime green, lambda 2 is the orange, and then lambda 3 is the blue. And you get the sequence of functions, which, you could do further analysis with. So you sort of map persistence diagrams into a Hilbert space, and it makes machine learning and statistics easier to work with.
Yeah, very good. And maybe just provide some more editorial comments. So this representation of the persistence diagram, when I think of every point above the diagonal is indicating a pair of scales. And, the whole theme of persistent homology is like, what is the rank of the map on homology when you go between those two parameter values? And so you can kind of denote this post set of intervals using the upper half plane above the diagonal. And then the sort of theme here is that we want to track jumps in this change of rank, and that's done via this persistence diagram. But traditionally we don't really think about these taking away points where you have like in green. But the landscape also provides a nice way of sort of turning diagrams into functions, which are easier to represent in machine learning methods. Yeah. All right. So I'll shut up.
No, thanks. Yeah. I guess, drawing it this way also, it kind of makes it pretty clear that actually what we're doing is exactly computing the persistence landscapes, right? So like when we draw this picture of just like throwing away everything of rank 1 and then throwing away everything of rank 2, everything of rank 3, it's pretty clear that these graded persistence diagrams are exactly corresponding to landscapes now, when you think of it that way. Right, okay, so yeah, so then our goal was to define distances between these things. So another bit of motivation, which Justin pointed out to me, and Alex McCleary's here today, so maybe he could tell us more about it, but McCleary and Patel defined the persistence diagram for filtrations indexed by finite lattices. So as the Möbius inversion of their birth-death function that they defined. And apparently these can take negative values as well. I don't have any intuition for what the negative values correspond to, but so, maybe at the end we could talk about that, because this might be an interesting connection to what we were working on. Another motivation is signed measures. So a lot of different people have considered signed Wasserstein distances. So in particular, Manini considers a bunch of different extensions of the Wasserstein distance to signed measures. So he's motivated by non-positive solutions to partial differential equations. So interestingly, he considers a bunch of them, discusses different properties, and he says there's no canonical choice of metric or extension of the Wasserstein distances. And so what I want, maybe in the context of PDEs, that's true. What I kind of want to say is that there kind of is a canonical choice, at least, categorically speaking. This distance that we've defined is sort of the canonical choice. Okay, so that's all my motivation. So, in order to talk about signed things, it's convenient to, use the Grothendieck group. So the Grothendieck group just takes a monoid and spits out sort of the universal group. So it's the group completion of a monoid. So formally, you have a monoid You form the Grothendieck group by sort of taking pairs and identifying them. So this is the formula. So you have x plus y prime plus k equals x prime plus y plus k for some k. In most of the settings that we care about, your monoid is cancellative, meaning x plus z equals y plus z implies x equals y. Okay, so if your monoid's cancellative, basically then this equivalence relation reduces down to, x, y is equivalent to x prime, y prime, if and only if x plus y prime equals x prime plus y. And the way you should think about this is indicated sort of by our notation. So we're going to denote the equivalence class of xy by x minus y. So we think of the pair xy as just, formally standing in for the difference x minus y. And then, with this notation, it's clear that this is exactly what the equivalence relation should be, because, if we have x minus y is equal to x prime minus y prime, then certainly x prime, x plus y prime should equal x prime plus y. Okay. And then, so this is a group. So the group operation is sort of defined in the obvious way. So you just, if you want to add two, differences, you just sort of take the difference of the components. And this is the sort of the universal group that you can get out of a commutative monoid. So, for any abelian group H and any monoid homomorphism from M to H, there exists a unique extension to a group homomorphism from the Grothendieck group to H. And here I is just the inclusion. So I sends, so I just sends M to M minus 0. And again, so this map isn't always injective, but if M is cancellative, I is always injective. So this, makes sense intuitively. And an equivalent way of saying this is we have an adjunction. So this map, which sends a monoid to its Grothendieck group, is actually functorial. And it's the left adjoint to sort of the obvious forgetful functor from abelian groups to commutative monoids. Excuse me. Okay, so examples. So kind of like the oldest example, which I'm sure predates Grothendieck, and he's not named for this construction, but so you can construct the integers from the natural numbers by the Grothendieck group construction. So I think this construction probably was around before Grothendieck, but it's named after him for the next example, which is for a compact manifold, you can consider the 0th K theory as the, so basically you take vector bundles or isomorphism classes of vector bundles with Whitney sum, and you take the Grothendieck group and you get virtual vector bundles, and that's sort of the main object of study in K theory or topological K theory. And so for us, why we care about the Grothendieck group is that we're going to take the completion of the space of persistence diagrams and study that object. So we call the Grothendieck group of the space of diagrams the space of virtual persistence diagrams. Okay, so our main question was, when does a metric on a monoid extend to its Grothendieck group? So we're going to answer this question in general. Maybe as stated, it's not quite well posed, because I mean, there might be many different ways to extend a metric to its Grothendieck group. So let me, set up the formalism so that we can answer this question in a well-defined way. So for us, our setting is going to be commutative metric monoids. So these are tuples. So it's a tuple MD plus 0, where MD is a metric space, which is also a monoid at the same time, and on which the metric and the addition are sort of compatible in the following sense. So D is one subadditive. Just means you could sort of break up addition like this. And then we can also define abelian metric groups analogously. So this third condition, so the first two obviously are what we want. The third condition, so we can motivate that as follows. So there's a tensor, like a product that you can put on the category of metric spaces. So back up. So if I want to take the one tensor between a metric space X and Y, this is just going to be X cross Y, and the metric we put is going to be sort of the sum of metrics. This being, so dx plus dy of xy, x prime, y prime is just sort of the component-wise distances, and then you add them together. And so this third condition is exactly saying that addition in this monoid is 1 Lipschitz with respect to this product, or this tensor. So it's a fairly natural condition, I think. And so the theorem, just a very general theorem, is that if you have a metric on a metric monoid, then this extends to a metric row on its Grothendieck group in such a way that the object you get is a metric group, if and only if D is translation invariant. Okay, so translation invariant is very important, plays a big role in being able to extend these metrics. And the proof is pretty simple. Like once you know the statement, it's just checking a lot of stuff, making sure everything's compatible. But essentially, this is the main formula that we use throughout. So if you want to define the distance between two differences, you just swap them. You just take the negative parts and move them to the other side, right? And so that's going to be a translation invariant metric on the Grothendieck group. Everything's compatible. You get a metric group. Conversely, it turns out that if you have a metric group, then rho is automatically translation invariant. So any metric on a metric group is translation invariant. And then you restrict it down to the monoid, it's also going to be translation invariant. Okay. So the takeaway is just if you have a translation invariant metric on a monoid, then you can extend it to the Grothendieck group. So for us, this is interesting. Well, so it sort of brings up the question then, when is the Wasserstein distance translation invariant? Let's see. Well, maybe, okay, I guess one more thing first. So to state this, as a universal construction, so we'll look at the category of commutative monoids internal to metric spaces. So these are just the commutative metric monoids we talked about, equipped with translation invariant metrics. And then this category here, so ABMET is the category of abelian metric groups. And actually this notation comes from the fact that these objects are exactly the group objects internal to the category of metric spaces, if you're familiar with that idea. And similarly, these are commutative monoids internal to the category of metric spaces. So there's an obvious forgetful functor. If you take, a metric group, you forget the group operation, or you forget the inverses, you get commutative monoids, and the metric is automatically translation invariant. And so basically our main theorem here is that the Grothendieck group functor actually, gets upgraded to a functor between these two categories, these two internal categories. So this extended Grothendieck group functor is the left adjoint of this forgetful functor. Cool. Okay, so let me do some examples. So simplest example, going back to the construction of the integers, which is, essentially trivial, but so what's the metric on the integers? It's just the absolute value metric. So you do, the distance between x and y is just x minus y. Okay, that's translation invariant and extends to a metric on z, but that metric is also kind of trivial. It's just, if you have a difference of two integers, which of course can always be written as just a single integer, but if we have like n minus m, n prime minus m prime, then the distance that you get from this construction is just, it's exactly what you would expect. It's stupidly trivial, but okay. But that kind of, is the simplest example. So for us, the one Wasserstein distance, it turns out, is translation invariant. And the other ones aren't. So for p greater than 1, you never have translation invariance, at least for in the settings we care about of persistence diagrams in the plane. So in particular, we get an induced metric on the space of virtual persistence diagrams defined this way, just by doing the swapping thing that I talked about. And more generally, the one Wasserstein distance between measures is translation invariant. So this is well known. This is this follows from Kantorovich-Rubinstein duality. And in fact, it's kind of interesting because when we first started working on this, you know, I wasn't super familiar with the measure theory, but at any rate, there wasn't really like a formal connection between the measure theory perspective and the persistence diagram perspective until Divol and Lacombe recently sort of made the connection formal. And so now the fact that the one Wasserstein distance between persistence diagrams is translation invariant follows immediately from their work, just by relating it to the classical measure-theoretic version. Yeah, so like I said, the p Wasserstein distances fail to be translation invariant for p greater than 1. And an easy way to see that is just, you know, take two diagrams with a single point. So maybe, so we have D and D prime, and we just pick a point in between them. It's like the midpoint. Let's call that, I don't know, P. So then, so if I look at the bottleneck distance between D, I'll just write plus for sort of union. More on that later, I guess. So the bottleneck distance between D and P and D prime plus P, so it's actually half of the distance between D and D prime, right? Because I can just match, let's do red. So I can match this point to the point P and this point to the point P as well. And then essentially half the distance. And I can obviously make this distance go to 0 if I just put more and more points in between D and D prime. And this also works for any P greater than 1 for the same reason. It's just easier to see with the bottleneck distance. Okay, and so so I guess why do we care about these metrics? Some of that's still work in progress, and some of it was proven in this paper. So if you have persistence diagrams D and E, then you can consider this metric where you you grade the persistence diagrams and you consider the graded distance or the signed Wasserstein distance between gradings, and you sum those together. So Betthauser and all, they prove that this metric that you get is more discriminative, and they define what discriminative means like formally. So so this metric is bigger than the one Wasserstein distance, and it's not by Lipschitz equivalent. So it's somehow spacing things out more, but it's a stronger metric in the sense that it's not just, you know, a scalar multiple of the one Wasserstein distance. And we're also thinking about more applications of this currently that we're working on, which I maybe talk about at the end. Okay, so part 2. So I guess maybe that would be a good time to like stop and see if you guys have any questions or comments.
I had a bad question, so I'll just wait for the good questions to wrap up.
I might have a bad answer. I don't know.
Alan, why don't you go ahead and kick us off and let all.
All right. So I know Bubenik because he taught at Cleveland State when I was a student there. So it's kind of cool to see his legacy continue. He probably forgot me years ago. I don't blame him. But I was really curious about your Grothendieck construction, because it does give you some more algebraic structure directly, but at K0 is also sufficient to start using the generalizations of like the Riemann-Roch theorem for the Riemann-Roch Grothendieck theorem. I was just curious if any interpretations of what that would mean have been considered, or if that was a direction that you guys had considered at all?
No. Okay. So yeah, it's a great question because I mean, we did consider it a little bit. In particular, so I know that you can define the K0 for like a graded ring. So I think you take like the Grothendieck group of the projective modules over that ring, and you can consider that space. And that's the K0 of a ring. And I think, so Nicola, so another person in our group who's here, so he kind of actually characterized the projective modules over the graded ring, which defines persistence diagrams. So you can think of persistence modules as modules over a graded ring, and then you can look at the projective ones, and then you can consider potentially the K theory that you get there. And we were thinking about whether or not that's the same as virtual persistence diagrams.
Interesting. I hadn't considered it quite in that direction. I was thinking more about statements that could be made by interpreting the Riemann-Roch theorem in this context, but that's also, that maybe that's what it was supposed to be. So that's interesting.
Yeah, I haven't thought about that direction. So I think that'd be interesting to at least look at and see if there's anything there.
Cool. Thank you.
Yeah, thanks for the suggestion. Yeah, anything else?
Another sort of dumb question, but does cancellative have any, does that imply translation invariance in any sense, or?
It goes the other way. So if you have a translation invariant metric, it implies that the monoid is cancellative. I don't think it goes the other way. Yeah.
All right. Cool. Yeah. Thank you for that. And I'll just say that direction which Nicola seems to be taking, it sounds super interesting. But I'll let you keep going with your story.
Okay. Thanks. Okay. Yeah. So part 2 is universality, and it kind of ties in a little bit. And actually, the universality came after the stuff we were working on here, because sort of just setting up all the category theory, we sort of saw this kind of nice result that popped out, and we got excited about that. We actually put that up first. So I kind of want to first introduce a different way of thinking about persistence diagrams, sort of algebraically. So for us, well, first off, we're going to generalize our settings. We're not just going to look at persistence diagrams in the plane. We're going to look at persistence diagrams on pairs of metric spaces. So we start with a metric, or well, in this case, just a set first, and then we'll equip it with a metric. So we start with a set X and a subset A. And then we just look at the quotient monoid, d of X mod d of A, where d of X is just the free commutative monoid on X. Okay, so basically, the free commutative monoid elements of that look like just finite formal sums of points in X. So really, it is just multi-sets. I mean, if you define them both formally, they're exactly the same thing, right? But it's just kind of a different perspective that we take. And an important special case, which just simplifies things a lot, is when we take A to be a single point, and then we kind of simplify the notation a little bit and just write d of X, X naught. So I think this is a nice perspective because, we can think of lots of different things that come up as just persistence diagrams in this setting or in this terminology. So barcodes are persistence diagrams where your set is the set of intervals of R, and then your base point is just the empty interval. Or you could think of rectangle barcodes as being persistence diagrams on the space of rectangles, with the empty rectangle being the base point. And so they all kind of fall into this setting when you think of it this way. And just real quick, I want to mention quotient metrics. And the reason is because, I could define everything, Wasserstein distance between X and A, or on X relative to A. But actually, it turns out if you just quotient everything down, you get a completely equivalent, definition that is easier to work with. So start with a metric space and a subset, and then you can form the quotient metric space so you define X mod A to just be the complement of X, or the complement of A union a single point. So basically just collapse A down to a point. And you define the metric on the quotient to just be so the distance here, let me draw a picture. So you have X, you have A. So the distance between 2 points, so you can either just take the distance between those 2 points in X, or you can take the distance of each point to A and sum those together. You take the minimum of those two quantities. So this is a metric space. And if you take a metric pair, so a metric space with a subset A, and you do this quotient thing, you end up with a pointed metric space. And so it's, we'll work exclusively with these pointed metric spaces because the monoid d of x A is isomorphic to the pointed, or the monoid you get when you consider this pointed set. So it's completely equivalent, and the distances we would get either way are they're isometric. Okay, so now let's restrict ourselves to pointed metric spaces. So diagrams on X are just, relative to this base point, are just formal sums of points, but technically they're quotient, or they're cosets, right? So, if I have alpha and beta of length n and m, I can pad these out by m copies of x naught to alpha and n copies of x naught to beta. So basically I'm just saying this is true mod d of x naught. Okay. And then we define the one Wasserstein distance as follows. So we just look at all permutations on n plus m letters. And then we look at the distance between AI and B sigma I. We sum all those distances together, and then we minimize over all possible permutations. So, I mean, this is exactly what we normally do, just a different perspective. So like we have, some number of points, and then what we're doing is we're just allowing as many points as we need at x naught. So think of x naught as representing the diagonal, to pad out these two diagrams so that they have the same number of points, and then we find a matching and we minimize over all possible matchings this cost. You could also define the p Wasserstein distances, but for simplicity, I just define the one Wasserstein distance. And so our universal result is that, so this space of diagrams with the one Wasserstein distance is the free metric monoid. So that means that for any other metric monoid and one Lipschitz map from your underlying space X to this metric monoid N, it should also be base point preserving, meaning it sends X naught to 0. There exists a unique Lipschitz monoid homomorphism from the space of diagrams to N. And moreover, the Lipschitz constant is preserved. Here, I is just sort of so it's just kind of the standard inclusions. What do? You take a point X and you map it to X, viewed as a formal sum with 1 point. So there's also analogous statements for the p Wasserstein distances, but it's a little more complicated to state, I guess. But so how's this tie in with that distance we have between virtual persistence diagrams? So basically, if you just compose these two universal properties, you get that virtual persistence diagrams with this extended signed Wasserstein distance is the free metric group on a pointed metric space. So in other words, another way of thinking about this is if you just take the free abelian group on a set and mod out by the base point, or the free abelian group on the base point, that's going to be the free metric group when you equip it with this signed Wasserstein distance. So then another thing that we consider in our paper that we want to explore more is that this idea also, can be applied to measures. So the measure-theoretic setting. So if you start with a metric space and a subset, why not just define the quotient of all radon measures, radon measures on X modulo radon measures on A? So we did that, and you can define a distance analogously. So what we call like a relative Wasserstein distance. So you look at measures in this quotient space, And then you look at the set of all couplings, pi superscript a. These are measures on x cross x whose marginals are mu and nu respectively, modulo measures on a. So all you do is modify to say, okay, like if you push down, project onto the first coordinate pi, you get mu up to a measure on a. So maybe you have to add some measure on a to both sides, but modulo that, the marginals are mu and nu. And then you define the cost exactly the same as you would for the ordinary p Wasserstein distance. And then we check that this definition actually generalizes the definition of Divol and Lacombe. So they only considered measures supported on open sets in Euclidean space. And so, this is a nice definition that applies to all metric pairs. So we think this could be interesting, or just simplify the definitions a little bit. Okay, so ongoing work. So I'm pretty sure.
Sorry, Alex, can I interrupt real quick?
Yeah, sure.
Should I go back a slide?
Yeah.
Right. I just want to take a little bit of time to marvel at this construction. So the coupling condition ends up being sort of weakened here because
exactly.
If you project down, you can always maybe you don't get exactly mu, but then you can pour some more sand on A to make up for it.
Yep.
I imagine there's some really interesting examples in that setting, but I don't have enough time. I haven't thought about them right now. But either way, maybe you guys do. Do you have any interesting examples where considering this?
Not really. We didn't go in too much detail into this, but it just seemed like a natural thing to include because we had this new perspective for persistence diagrams, and we realized, might as well try it for measures, and this is what we got. But I think there's definitely more work to be done and connections to be made. Yeah.
Yeah, I mean, one natural setting is there's this distances between trees, and trees themselves are metric spaces, and so then you can use sort of a Gromov distance between two trees by trying to couple through all possible metric spaces. But the question is sometimes when is that coupling metric space itself a tree? And I'm wondering if there are situations where pouring or allowing yourself to pour some mass somewhere else in the tree allows you to marginalize in other ways or interesting ways. This is just unformed ideas, but all right, either way, keep going. Sorry.
No, that's a good point. I'm almost done, so it's okay. Yeah, that'd be interesting. Yeah, so ongoing work. This is my last slide. So universality, I think this should extend to the previous slide. So our universal results for the Wasserstein distance for persistence diagrams, I think something like that holds for measures, and pretty close to getting a statement like that. But there's some technicalities, measure-theoretic technicalities that come up, and so you have to be really careful. But I think there should be a nice statement there. So an application of these signed Wasserstein distances that we're working on right now is to try to strengthen some of the topological properties that we have for the Wasserstein distance. So it's known that the space of diagrams, just ordinary persistence diagrams with the Wasserstein distances aren't locally compact. But we think that by sort of considering the sums of these graded diagrams, we might get stronger topological properties. So if not just the sums, maybe a weighted sum of, so in other words, maybe do something like consider distances of the form. So distances of this form, where you do sort of a weighted sum of the one Wasserstein distances between the corresponding graded diagrams. So we think that maybe by choosing carefully the C sub k, we can actually get better topological properties. also along those lines, maybe we're thinking that you might be able to coarsely embed signed Wasserstein distances into Hilbert spaces in some sort of way analogous to this, where we choose some weightings. So that's interesting because Alex Wagner proved that there's no coarse embedding for p greater than 2 of the space of diagrams equipped with the p Wasserstein distances into a Hilbert space. So I think the question's open for p between 1 and 2. I forget inclusive or not. But this would give us, he suspects that that's not true, I think, last time I talked to him, for any p. But this potentially would give us, it'd be like a consolation result that, there is some coarse embedding in some sense. So that's it. Thanks for listening.
Great. And I'll encourage people to mute themselves and give Alex a round of applause. All right, cool. So I'm going to stop recording.